And welcome students. This is a lecture on application of derivative and we are doing in that maxima and minima. We are starting with maxima minima today. Before this earlier lecture, I had completed increasing and decreasing function. That was the basis of the topic maxima and minima. After that, we normally start with maxima and minima. So the topic is maxima and minima. Remember students, when we say maxima or minima, what we mean is maximum of a function. I will teach you everything right from the scratch. So I will take you in the topic in such a way that you will keep understanding each and every minute thing, minute details about the topic. So maximum, when I say maxima or minima, maxima and minima, what we mean is maximum of a function. We mean maximum of a function and minimum of a function and minimum of a function. This is what we mean. When we say maximum, when we say maxima, maxima is what we mean is maximum of a function. By minima, we mean minimum of a function. Now, why use maxima? See, maxima is plural. Maximum is a singular word. Okay, it's a singular. Okay, single function, single maximum. Okay, but then if you have more than one maximum, then you call it maxima. When you have more than one maximum, you call it as maxima. Okay, it is plural. Same way here, when you have more than one minimum, you call it as minima. Okay, as we will enter into the topic, you will understand that a function may have more than one maximum. Yes, a function may have more than one minimum. As we will enter into the topic, we will come across all these details. So students, we have covered increasing and decreasing function in the earlier lecture. So think of a function which is an increasing function. So think of a function in the interval a to b. In the interval a to b, think of a function which is an increasing function. So if I have a function like this, see, in the interval a to b, this is say y equal to f of x. This function is an increasing function in the interval a to b. In the interval a to b, this function is an increasing function. But remember, this function has the maximum value. This function has the maximum value in the interval a to b as this. See, this is the maximum value of the function in the interval a to b. And here this one is the minimum value of the function in the interval a to b. Okay, this value is the maximum value of the function in the interval a to b, and this is minimum value. The maximum of the function y equals to f of x is occurring at x equals to b, and here it is occurring, the minimum is occurring at x equals to a. Now understand that this maximum which I got, I will call it as absolute maximum. I will call this maximum as absolute maximum. I will explain everything why this is absolute maximum. Absolute maximum of f of x, that is function y equals to f of x, at x equals to a, and absolute minimum of f of x at x equals to, I'm sorry, I made a mistake. The absolute maximum is at B. The absolute maximum is at B and the absolute minimum is at X. X equals to A. Now, what is that absolute maximum value? The absolute maximum value is f of B. That is, to get the absolute maximum value of f of x, you will put x equals to B here. That is f of B. And where is that f of B? F of B is a number on y-axis. See, this number is f of B, which is absolute maximum. And this number is f of A, which is absolute minimum. The function value is always taken on the y-axis. This is absolute minimum. Now remember, students, here let me write absolute minimum of f of x is f of A. Okay, absolute minimum value is f of A. Now remember, students, the function, as you notice, it is going beyond the function, as you are noticing, it is going beyond the interval A to B. Now the thing is, I'm not concerned about the function. I'm not concerned about the function before A and after B, because that is what I decided. Okay, absolute maximum of the function, absolute maximum of f of x at x equals to B. Now I'm not concerned about the function beyond this interval. Okay, so here I can write a function. I can write here, consider a function, y equals to f of x in the interval, in the closed interval A to B. Now when I write like this, remember, I'm not concerned about the function beyond this interval. Beyond this interval, I'm not concerned. That is, before x equals to A, what is happening to the function, and after x equals to B, I'm not concerned about it. But in this interval, I notice that maximum is at x equals to B and the minimum is at x equals to A. And the minimum is at x equals to A. Okay. Now you have a question in your mind that why do we say absolute maximum? Why not simply say maximum? Okay, that I will now make you understand. Why do we say absolute maximum? One by one, you will get the idea. Let me now take you to the next discussion where, see, y-axis, x-axis, the interval once again A to B. Okay, I'm concerned with the function. I'm concerned with the function in the interval A to B. This is A, this is B. And now this time I have a function, and see, that function goes like this. See, the function goes like this. Now here what I understand, okay, see this function, let me call this function as y equals to g of x. Now here y equals to g of x, once again this function might be present even after B and before A. I'm not concerned with the function before A and after B. I'm only interested in the function in the interval A to B. This is y-axis, this is x-axis. Okay. Now, unlike the previous function y equals to f of x, this function was monotonically increasing. It was increasing, 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 and only increasing. This function we say strictly increasing in the interval a to b. But here what you are understanding, you understand that the function is increasing and then you know it reaches its peak somewhere here. Here it is reaching the peak. After that, the function reaches the peak here, and after that, the function starts decreasing. See, it is decreasing, decreasing, decreasing. And then once again, it reaches its lowest value. And after that, it starts increasing again. Again, it starts increasing. Now, what is happening in such cases? The function changes its behavior. The function is changing its behavior at 2 points. These 2 points are called as the turning point. See, this is one turning point. This is another turning point. Okay. So I may call this as, let me call this as C, this point as C. So I will call this as x equals to C. And this as x equals to d. On the x-axis, these are two numbers. So I notice that x equals to c, the function before x equals to c, from a to c, the function was increasing, and after c to d, it was decreasing. So in this interval, I understand that the function is increasing, right? And in this interval, I understand the function is decreasing. Then again, it starts increasing. Now look at the behavior of the function. When a function is increasing and after a certain point, it starts decreasing, mathematically, we say that the point where up to which the function was increasing and then started decreasing, the function is said to be maximum at that point. The function is said to be maximum. The function is said to be maximum at that point. The function is said to be maximum at that point. So function was maximum at this point C. Remember, the function was maximum at C. And remember, students, this maximum is, it is not absolute maximum. It is a local maximum. We call it as a local maximum. Local maximum. And here, this point up to which the function was decreasing, and after that it started increasing. The function was decreasing up to this point. This point it was decreasing up to this point it was decreasing, and then it's after that it started increasing. So we say that at this point the function has a minimum value. So minimum at that point, minimum at that point. So the function has maximum at this point and minimum at this point. Again, this is not an absolute minimum, it is a local minimum. So in this interval, when I say what is the absolute maximum, so you will have to find that for this function y equals to g of x, see the value of this function y equals to g of x in the interval a to b, you project on y-axis. So let us project this whole function on y-axis in the interval a to b. So see here, the function starts from this point. The function is starting from this point. In the interval a to b, the function is starting from this point. See, the function is starting from this point in the interval a to b, and it is going up to this point, right? The function is starting from this point and it is going up to this point. So let us project the whole function from here to here. Let us project the complete function on y-axis. Okay, for the value of the function, what we do, we project it on y-axis. So let me now project it on y-axis. So I'm projecting the function on y-axis. See, I project it. So when I projected, see what I got. I got this as the absolute maximum and this is absolute minimum. Try to understand. This point, this value is absolute maximum. Absolute maximum. Okay, and this number is absolute minimum. Absolute minimum. Now, other than these two values, see, this is here absolute minimum, this is absolute maximum. Other than these two values, we still have maximum. This is local maximum and local minimum. Okay, I will now take one more case to make you understand this still better. Still better. Just do not worry, I shall explain each and everything in detail and with all the concepts. Have patience and keep listening. See, this is interval A, this is interval B. So here I have A to B. Suppose I have a function in this interval which goes like this. The function goes like this. Now what we notice? We notice that this is f of A, this is f of B. The function is changing its behavior at 3 points this time. See, this is 1 point, this is second point, and this is the third point. Okay, I call them as C, D, and E. I notice that function before C, sorry, the function I noticed before C, after A, it was increasing, it was going up, and then at C, the function has its maximum value, and this is definitely f of C. Where would you project to get the value f of C? Here, see, this is f of C. This is f of C. Because the function, yeah, definitely, it is needless to say that function I took as y equal to f of x. So definitely when x is C, the y value is f of C. And where is f of C? So this number is f of C. And I will call this number as of now, it is local maximum. Okay, it is a local maximum, right? And here we have the minimum. This is minimum again. Remember, it is minimum. Why minimum? Because the function was decreasing. You see, the function was decreasing at C. See, the function was increasing after A. But did it increase forever? No, it did not increase forever. There was a point after which it started decreasing. So after increasing for certain values of x, for these values of x, the function was increasing. After a point when it started decreasing, so that point we say that it is the point of maximum. It is a point of maximum. We also call it as turning point. C is a turning point. We can call it as point of maximum. There are several terminologies. I'm trying to cover each and everything. Point of maximum. And then after this point of maximum, remember the point of maximum is achieved. The point of maximum is achieved only after increasing when decreasing happens. The function was increasing and then it is decreasing. So the point of maximum will appear. See, every time the shape will be like this. This will be the shape for point of maximum. For point of maximum, this will be the shape, always like this. Okay. And then here we have point of, see, then it started decreasing. Did it decrease forever? No. At one point, it it decreased up to certain level at one point, and after that it again started increasing. This is known as point of minimum. I call this as point of, I call it as point of minimum. Point of minimum. And then again I'm reaching point of maximum. See, again here I'm reaching point of maximum. So what you understand that there are 2 points of maximum. Yes, what you are saying is true. There are 2 points of maximum. Now see, this is something which normally troubles students. Okay, this is something which is not, which normally troubles students. There are 2 points of maximum. Okay, this is something which normally troubles students because they think they are literally taking the word, they are taking the word maximum literally. Please do not go by the literal meaning of word maximum. When we say maximum, we thought that there can be nothing greater than that. Now here you would actually be those who are doing maximum minimum of a function for the first time. They are amused to know that we are having 2 maximum. How is that possible? But remember students, this is all local maximum, local minimum. I will give you an example for this. Suppose in your school there are several divisions. Okay, there are several divisions and there was one exam conducted on mathematics. So this is division A, division B, C, D and E. So there are several divisions and one exam on mathematics was conducted for 100 marks. Now in division A, the maximum which was obtained in division A was 82. In division B, it was 76. In division C, it was 89. In division D, it was 63. And in E, it was say 75. So now what you see? You see that, can I say 82 is 82 is maximum? Yes, it is maximum, but it is maximum for division A. It is maximum in division A. Amongst those, say in each division, say there are 30 students. In each division, you have 30 students, right? So what we can say here is that amongst these 30 students, the one who got 82 is the maximum. And amongst these students, 76 is maximum. But if you go for the absolute maximum, so see, these are all local maximums. Maximum in that particular division. But which is the absolute maximum? 89 is the absolute maximum. Amongst these 5 divisions, now once again, this 89 is absolute maximum amongst the 5 divisions of that school. If the same paper is given to some other school, then there could be another student who might get marks greater than 89. And there could be some students who may get even more than that. So remember, in this school, What is the absolute maximum? In this school, the absolute maximum is 89. Other than this 89, if I consider the individual divisions, then we have local maximums. 82 is local maximum, this is maximum, this is maximum, this is maximum, this is maximum in respective divisions. And 89 is absolute maximum. So this was the example for maximum. Similarly, we can have an example on minimum also. I can have an example on minimum. Say the minimum marks obtained in division A was, the minimum marks was 50. And in division B, the minimum marks was 55. And in C, the minimum marks was 70. In D, the minimum marks was 45. And in E, it was 40. So now what you notice that 50 is the local minimum. In division A, it is minimum. Is 50 the absolute minimum? No, the absolute minimum amongst these 5 divisions occur at 40. So this is what the idea of absolute maximum and minimum are. I hope you followed it. Still, you shouldn't be worried, because as we are progressing, you will understand much more about it. So here we have 2 points of maximum and 1 point of minimum. Remember students, there is no hard and fast rule. There can be any number of maximums and any number of minimums in an interval considered. Like I considered the interval from A to B. Before A and after B, I'm not worried. I'm not bothered. Okay, before A and after B. Now, once again, what I do is I want to get, see, you got the point of maximum and minimum, and these all are the local maximums and local minimums. Okay. See, once again, I will project this point also and on y-axis, because for the function value, we always see the y-axis. For the value of f of x, I will see y-axis. And at what values I'm getting those functions value, for that we will see the x-axis. So at x equals to e, the function has a maximum. So what is that maximum? F of e, x equals to e. Now at x equals to d, the function has a minimum. And what is that? It is f of d, which is the minimum here, right? Now, I do have f of a and f of b also, definitely. Let us project them too. Okay, see, this is f of a and here f of b, right? I do have f of a and f of, sorry. This is f of a and f of b. But unlike the earlier example, you can check. See, in earlier example, f of a was the absolute minimum. You see this? This was f of a. And here this was f of b, which was the absolute maximum. The point of maximum, the local maximum where occurred. Okay, the point where the local maximum occurred, what we noticed, that was lesser than the absolute maximum. Okay, and the point where the local minimum occurred, that was greater than the absolute minimum. Okay, but here the case is a slightly different. See, once again, what I'm doing is I will project, let me project the function value on y-axis. Okay, so it is starting from a to b. So see, everything that in the interval a to b, everything, every value that function assumes, every value that function assumes in the interval a to b, I'm projecting it on the y-axis. I'm projecting it on the y-axis. Okay, so when I do it, see what I got. I got here See, I got here the absolute maximum. What is the absolute maximum? The absolute maximum I got at this point. Remember, try to understand the absolute maximum is happening at this. This was a local maximum. Try to understand this was a point of local maximum at C. Definitely in the vicinity of C, in the close neighborhood of point x equals to C, it is maximum, but that happens to be absolute maximum also. That happens to be absolute. See, no, this is the highest value that function attains in the interval a to b. Okay, and see, there is one point of minimum here, but then there is another value of function which is even minimum that local minimum. See, this is local minimum, this is local minimum, where the function has local minimum at point D. But what you notice that there is one value of function in the interval a to b which is still lower than that. So this is absolute minimum. So here you have absolute maximum, and this is absolute minimum, absolute minimum. But if I ask you where the function has local maximum, local minimum, then there are three places. Two places for local maximum. See, this is local maximum. This is also local maximum here. This is also local maximum, and this is local minimum. Okay, but where is absolute? Absolute maximum will be just one value. Remember, you can have several local maximums, you can have several local minimums, but there will be only one absolute maximum and absolute minimum. The absolute maximum means you cannot have any value of function greater than that. Absolute minimum means you cannot have any value of function lesser than that in that interval. That goes without saying. Okay, students, so here let's go ahead for some more discussion. I have an interval, I have a function in the interval a to b. Okay, now in this function, let us call this function as y equals to h of x. This function is, say, y equal to h of x. Now in this function, I have several maximums and minimums. Okay, I have several maximums and several minimums. So here I see, look at the shape of the function. Whenever you see such a shape in the function, okay, you should understand, like a dome shape. Okay, if you see something like this, so it is the function is having a local maximum at this point. See, again, here also maximum, then maximum, then here also maximum. Okay, so function is having 1, 2, 3, 4 places where it has maximum. And those points, you know, where the function has such a shape, see this one, it is known as minimum, the point of local minimum, such a shape, the point of local minimum. These are all local maximums and local minimums. Now, one thing I would like to say here, that see, you please understand that conventional meaning of maximum and minimum, it does not work in mathematics. Why? Because you can understand, look at this point where the function has minimum. I'm talking about, okay, first of all, let me name these points. These are all turning points. First of all, I will name them all. So this is, say, point, this is C, this is C, this is D, this is E, this is I, this is J, this one is K, this one is L. Okay, so see, at I, look at that function. At I, the function has a y equal to h of x. At I, the function has a minimum. Okay, the function has a minimum value at I. There are several minimums it has, but one of the minimum is at I. See, it also has a minimum at D. It also has a minimum at D. It has a minimum at K, and it also has a minimum at M. Okay, see, it has a minimum at M also, right? This is point of minimum. It has a minimum at M also. Now see, this value which you have, it is, what is the minimum at I? F of I is that minimum value. The function has a local minimum at I, and that is f of I. The function has a local minimum at D, and that is f of D, that minimum value. The function has a local minimum at K, which is f of K. The function has a local minimum at M, which is f of M. Okay. But what I want you all to notice is, I told you that please do not go by the conventional meaning of maximum and minimum, because this is all local maximum, local minimum. Look at the function. The function has a maximum at L. You see this? The function has a maximum at L, and that maximum is f of L. That maximum is f of L, and here it is, see, f of L. But you will be surprised to notice that maximum at L is lesser than the minimum at I. See, f of L, where is f of L occurring? F of L is occurring, see, this is f of L value on y-axis. You see this? And what is f of I? F of I is actually a minimum value, local minimum. But you are noticing that local minimum is a greater value than local maximum. See, this is minimum value, but it is above the maximum value. Okay, minimum value is above and maximum value is below. Okay, so please understand that all this is local maximum and local minimum. What we want to say here is, in the vicinity of L, in the close neighborhood, of L, that is, when you go very little to the right of L and very little to the left of L, the maximum is at L. Just before L, the function was increasing behavior. The function was an increasing behavior just before L, and just after L, it was a decreasing behavior. So we say that at L, it is having its maximum. Okay. Now one more word I'm going to toss before you, and that is, it is also said that function is supposedly stationary at L. The function was stationary at L. Before L, the function was increasing. After L, the function was decreasing. And at L, at x equals to L, the function was stationary. It was stationary. It was still. I can give you an example for this. For example, suppose you are standing on ground. You are standing on ground here, and okay, there is a boy who is standing on the ground, and he has a stone in his hand, and with all force he throws the stone up. So the stone goes up, 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 up. Will the stone keep going up forever? No, that will not happen. It all depends on the force with which he threw the stone. After one point, the stone will start coming down. Okay, so what was happening? See, the force that he applied, when the amount of the force he applied was greater than the gravitational pull of the earth, the stone was going up. But after certain time, the the gravitational pull of the earth increased the force that he applied. So what happened? After that, the stone started coming down. But at one point, the stone would have been still, stationary. Okay, at one point, the stone would have been still, stationary. Okay, it would appear to be stopped, at rest. It would appear to be at rest. And then after that, it will start coming down. It will start coming down. So this point is known as the point of stationary. Okay, I hope you all are following this. So here we say the function is supposed to be stationary at L. Okay, so all those points, the function has a turn. See, all the turning points. So at point C, again, at point C, the function is stationary. The function, these are the points where the function is stationary. These are the points where the function is stationary. Stationary at C, stationary at D. See, why stationary at D? Because just before D, the function was in decreasing nature. The function was a decreasing nature just before D. But after D, it started increasing. So there is a change in the behavior. It means at D, it supposedly was stationary. It was stationary at D. So what more points it is stationary? See, the function is stationary at E. It is stationary at I, at J, at K, at L, at M. These are the points where it is stationary. So the function is stationary at these points, which are also the turning points. Point C, point D, point E, all are also known as the turning points. So students, now look at this curve y equals to h of x. And now one thing which I want to add here is that if I draw tangents to this curve, now we all have done already, we have done tangents and normals to the curve. I just want to add one thing, that all these points, which are the turning points, x equals to C, D, E, which you see on the x-axis, these are the turning points where the function is changing its behavior. Like at C, it was increasing before C, but after C, it started decreasing. So C is the turning point. D is the turning point because before D, it was decreasing and that started increasing. Now, what I'm trying to tell you is, if I draw tangents to this curve at the turning point, say I draw a tangent to the curve at C, and then I will notice that the tangents are coming parallel to x-axis. See, I am not deliberately trying to make it parallel to x-axis. They are on their own coming, all the tangents are coming. If you draw a tangent to the curve, you understand the meaning of tangent? Tangents are lines which touch the curve. So if I'm trying to touch the curve by a straight line at these turning points, what I'm getting is automatically I'm getting parallel to x-axis. I'm getting parallel to x-axis. So these all tangents are automatically coming on their own parallel to x-axis. This is a very important property which we are going to apply for maxima and minima. Okay. So remember, wherever the function, this is the property that we are going to apply. Wherever a function has maximum or a minimum, wherever a function has a maximum or a minimum, if a tangent is drawn to the curve at that point where it has maximum or minimum, the tangent would come parallel to x-axis. The tangent would come parallel to x-axis. The line which is touching the curve at the point where it has maximum or minimum is parallel to x-axis. Now you understand, if this all tangents are parallel to x-axis, these all tangents will have slope equal to 0. So automatically the slope of these tangents will be 0. Why? Because any line which is parallel to x-axis has slope equal to 0. Now this idea we are going to use. Okay. Now here check. I have drawn a function y equal to f of x here. I have drawn a function y equal to f of x, and now here the curve which I have drawn, deliberately I am taking only the shape where the function has a local maximum. Okay, see, you check this dome shape here, because I am deliberately taking a small portion of the curve, because now we are going to deal into the topic. So we are entering into the topic. So I'm going to derive few concepts so that we can start solving problems. So I'm taking deliberately a small portion of the curve. Okay, say this is y equals to f of x, and the function has a local maximum at a. At a, it has a local maximum. And then just before a, very small distance I take h. Now here h looks quite big, but then I have to take the liberty for teaching. This h is so very small that it is tending to 0. Okay, and so before h, this point will be before a. Before a, at a distance of h, I will have here a minus h, and here I will have after a at a distance of h, a plus h. Okay, so this is what I have. Now see what I do next. Now here, now look at this. I draw a tangent to this y equal to f of x. I draw a tangent to y equal to f of x. At x equals to a, where the function is having its maximum, local maximum. The function has local maximum at x equals to a, right? This is the maximum value, which is f of a. What is that value here? It is f of a. So this point is f of a. Okay. Just before a, that is at a distance of h, the function has a value which is f of a minus h. Remember students, this is f of a minus h. And this side it is f of a plus h. And mind it students that f of a minus h and f of a plus h, they are both lesser than f of a. They are both lesser than f of a for sure. That is why in the closed neighborhood, we say that the function is having maximum at a. Okay, so I may wish to write it here. I write here f of a is greater than f of a minus h. F of a is greater than f of a plus h. Okay, right? Therefore, the function f of x has a local maximum. No need to write local, it is understood. Right, maximum has a maximum. It has a maximum at x equals to a. Okay. I drew a tangent to the function. I drew the tangent to the curve, at x equals to a. I want the slope of this tangent at x equals to a. You all know the slope of the tangent will be, f dash a. How do you find the slope of tangent? Sorry. How do you find the slope of the tangent? You will differentiate the function. So y equal to f of x. When you differentiate, you get dy by dx equals to f dash x. Now, You substitute the value of x in this in order to get, if you want the tangent, if you want the slope of the tangent at x equals to a, you substitute x equals to a. I want the slope of the tangent at this point. So what I would do, what are the coordinates of this point? The tangent where you draw to the curve, the coordinates are a comma f of a. So you want the tangent at a f of a. What would you do? In this, you will substitute the coordinates. Now there is no y, so no need to go for y coordinate. There is only x. So x is a. So you substitute x a and you get f dash a. So what is the slope of the tangent at x equals to a? It is f dash a. And what is f dash a, students? F dash a is equal to 0. The slope of the tangent of this, the slope of this tangent, the slope of tangent at a is given by f dash a. And since I understand that this tangent is parallel to x-axis, its slope value is equal to 0. Its slope value is equal to 0. Now, next, I go for two more tangents. See, I go for a tangent at x equals to a plus h. Okay, let me go for a tangent at x equals to a plus h. So here I have a tangent at x equals to a plus h. I want the slope of this tangent. Very simple. If you want the slope of this tangent, what would you do? You will substitute the coordinates of the point where the tangent is drawn in dy by dx. What are the coordinates? The coordinates are a plus h, comma, a plus h, comma, f of a plus h. X coordinate is a plus h, and y coordinate is f of a plus h. So when you substitute, what you get f dash. See here, in this, when you substitute the coordinates, x is a plus h. So you get f dash a plus h. You get here f dash a plus h. So slope is, see, the slope is f dash a plus h. F dash a plus h is the slope. Okay. And remember, students, this f dash a plus h is lesser than 0. It is lesser than 0. This slope which I got is lesser than 0. How do I know it? See, I will tell you that. I will make you understand. Look at this tangent. This tangent is cutting the x-axis at this point. And the point where it is cutting the x-axis, if you measure the angle it is making with the positive direction of x-axis is obtuse angle. It is obtuse angle. This angle is the inclination theta, angle made by a line with the positive direction of x-axis. And I understand this theta is greater than 90 degree. If you have the inclination of a line, its slope you give by tan theta. So tan theta would be slope. But you see that this theta is greater than 90 degrees. So tan theta will be lesser than 0. Slope is lesser than 0. For this line, the slope is lesser than 0. F dash a plus h is lesser than 0. Now let me go for the third tangent. I will draw one more tangent. At this time, the tangent I draw is at a minus h. I draw a tangent at a minus h. I draw the tangent to the curve just before. See, what was this tangent? It was a tangent to the curve just after where the function had maximum. What is this tangent? This tangent is tangent to the curve just before it has maximum. Where the function has a maximum, the tangent has slope 0. Where the function has maximum, the tangent has slope 0. Just after that, the tangent you draw, the slope is negative. And here, you know, students, what would happen? Let's check this also. See, I will the slope of this tangent, would be given by f dash a minus h. The slope is given by f dash a minus h, because to get the slope you will substitute x equals to a minus h here, and this f dash, this slope is greater than 0. This slope is greater than 0. How do I know? Because see, this tangent is cutting the x-axis here, and where it is cutting the x-axis, if you measure the angle, this angle alpha is the inclination, which is the angle made by the line with the positive direction of x-axis. And what you notice that this alpha is lesser than 90 degree. It is lesser than 90 degrees. So slope, which is tan theta, that is tan alpha here, if the alpha is lesser than 90, tan alpha will be definitely greater than 0. So slope is greater than 0. So here, so you all understand, students, that the function, see, now we have the concept which we are going to use for solving problems. The function y equal to f of x. See, the function y equal to f of x has its maximum at a point where the first derivative is 0. Okay, the function y equal to f of x will have maximum at a point x equals to a, then the first derivative will be 0 at a. You can check f dash a is 0. Just before a, the derivative will be positive. You can check just before a, the derivative is positive, and just after a, the derivative is negative. So this is the condition for a function to have maximum at x equals to a. So here I write maximum of a point. This is the heading. Maximum of a function. The heading is maximum of a function. And what is the condition? Just now I stated. See, I stated the condition that a function y equal to f of x has maximum at x equals to a when at x equals to a, the first derivative will be 0. Just before x equals to a, that is at x equals to a minus h, the derivative will be positive, and after x equals to a, just after x equals to a, that is at x equals to a plus h, the function has derivative negative. So remember, if the derivative goes from positive to 0 to negative, the derivative goes from positive to 0 to negative, the function has a maximum at that point. Okay, the function has maximum at that point. So I will write the pointers. I will write the condition here. So here I write, see, a function y equal to f of x has a maximum at x equals to a if f dash a is 0, f dash a minus h is greater than 0, and f dash a plus h is lesser than 0. Okay, see here, students, I will now make you understand this so that You will not have to worry to remember this. Okay, you will not have to worry to remember this. See how does it go? It's very simple. It's very simple. See, for maximum, how does it go? Maximum is always, maximum happens always when the curve has the shape this way. You will all agree. The curve has the shape this way. Then only here the maximum happens. Okay, so remember, for maximum, here it will be, derivative will be 0 because the tangent is parallel. Okay, and then what? See, this way, look at the curve how it is going. This way, then then this way, then this way, then this way. You see this? Then this way, then this way, then this way, then this way. So try to understand why is that curve coming? Why the shape of the curve is that way? It is because why do we have this shape? Why do we have the shape of the curve at maximum that way? It is all because of the tangents. Look at the trace of the tangent, you will understand. Look at the trace of the tangent. Okay, even if I remove the curve, you can imagine that had the curve been there, it would have definitely fit in to give the maximum. It would have definitely, see how does the curve go? Okay, how does the curve go? It is this way, 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 and this. So it is finally giving us what? It is giving us maximum. So remember, you have to start like this, and all these tangents will cut x-axis at acute angle. So if it is cutting at acute angle, tan theta will be positive. So slope positive, before positive, at 0 after negative. Remember like this. Okay, before positive, then at 0, and afterwards negative. So this is condition for the maximum of a function. Okay, I hope you followed it. See, to find the maximum of a function by this method, which I just taught you, it is known as first derivative test. It is known as the sine of first derivative. This is known as sine of, wait, sine of first derivative. Sine of first derivative test. So by the sine of the first derivative, you just saw here, I'm deciding that the function is having maximum at x equals to a. And how am I doing it? I'm doing it with the help of the sine of the first derivative. See, at a, the function is having its first derivative 0. Just before a, the sign is positive. See, it is greater than 0. And just after a, it is negative. Now we are going to have the second derivative test. Okay, so I will give you now the second derivative test. So here I will write sine of second derivative test, which is normally used for solving the problem. See, I have taught you the first derivative test also, but normally we are not using the first derivative test. We are using only the sine of second derivative test, because comparatively the second derivative test is easier than the sine of first derivative test. So I'm going for sine of second derivative test. Okay. So see here, students. I notice that function has maximum. Look at the diagram. I notice that the function has maximum at x equals to a. The function has maximum. It is quite evident from the diagram. The function is maximum at x equals to a. Wherever there is a function having maximum, it would have the shape like this, and then it will be maximum at this point. Now, what I understand here is at a the function has derivative 0, f dash a is 0, f dash a plus h is negative, and f dash a minus h is positive. Okay. Now, students, by Newton's first principle, okay, by first principle of derivative, see here, we all know that by first principle of derivative, students, we all have studied that f dash x, if you want, then it is f of x plus h. F dash x is f of x plus h minus f of x upon h, and limit of this when h tends to 0. What is f dash x? If you want the derivative of f of x, if you want derivative of f of x, then what do? You find the value of the function at x equals to x plus h. That is, you slightly increase the value of x, see f of x plus h. Then you subtract the original value, that is f of x. So f of x plus h minus f of x, and then you divide the whole thing by the increment in x, and you find out the limiting value of that when h tends to 0, right? That is, the increment tends to 0. This way you get the derivative of f of x. But suppose I want derivative of f dash x. What would I do? I want derivative of f dash x. Yes, you heard me right. I don't want derivative of f of x. Derivative of f of x I already found. I found it as f dash x. Now I want derivative of f dash x. So derivative of f dash x will be f double dash x. Yes, I want this. Listen. For finding the derivative of f of x, what did you do? You increase the value of x by h, and then you subtracted f of x plus h by f of x, subtracted f of x plus h by f of x. Now, same thing you would do for f dash x. So see here, f double dash x will be limit h tends to 0. See, now you will not write f of x plus h. You will write f dash x plus h minus f dash x upon h. And if you want this f double dash x at x equals to a, suppose you want it at x equals to a. So now you substitute x equals to a. So f double dash a would be limit h tends to 0. You are substituting x equals to a. So you will get f dash a plus h minus f dash a upon h. And what would you get here, students? See, you will get that equal to so f dash a you would get f double dash a is, see, limit h tends to 0. See, for the maximum, what is f dash a plus h? Tell me, what is this? It is negative. You can check. See, f dash a plus h is negative. It is less than 0. It is negative. So here you would write negative. We are working for the case of maximum. And what is f dash a? F dash a is 0. F dash a is 0. See? So negative minus 0 upon what is h? H is the distance between these 2 points. H is always positive. H is always positive. So negative minus 0 upon positive. So what you would have, negative upon positive. See, negative minus 0 is negative and negative upon positive is negative. So see students, what you will get is a negative value. So f dash a, f double dash a is less than 0. F double dash a, the sign of second derivative, you got negative. So students, see, now you have made it. You have made a point. What? For a function to have maximum at x equals to a, for a function to have maximum at x equals to a, the second derivative test would be f dash a should be equal to 0. The first derivative at a should be equal to 0. And the second derivative at a should be less than 0. This is second derivative test. See, for first derivative test, what happened, you know? You needed three derivatives, one at a, one at before a, one at after a. But in the second derivative test, it is very simple. You need only two derivatives. Like first derivative at a and second derivative at a. If the first derivative at a is 0 and second derivative at a is negative, the function is maximum at that point. So I will now write the final statement, and that will be all for this lecture. See here, I write a function f of x, a function f of x is said to have a maximum at x equals to a if f dash a is 0, first derivative has to be 0, and f double dash a has to be negative. So we are going to use the second derivative test for solving problems. You will all copy it down. Lecture, as I took the case of maximum of a function, in the next lecture I will take the case of minimum. That is, I will have the function like this and I will do this whole analysis, and then after that we will solve problem on these maximum and minimum of a function. I hope you all followed this.